We have ended lesson 2 by defining the concept of basis of a vector space, which is easily one of the most fundamental of the entire linear algebra. We have also provided the easiest example of basis for the easiest vector space that we consider so far, that is Fn, where F is the field of real or complex numbers. This basis is shown here and it's called the canonical basis of Fn. Let's start lesson 2 by showing what is the special feature of this basis, considering the case n equal to 3 to avoid useless computational complications. The canonical basis of R3 is written here, and it's composed by vectors e1, e2, e3, which have all null components except for the one that corresponds to the position indicated by the index that labels these vectors. As always, we indicate the generic vector of R3 with x, y, and z, with x, y, and z free to vary in R, and then we consider the vector equation in which we equate the vector v with the linear combination of the vectors e1, e2, e3 of the canonical basis of R3 with the components lambda 1, lambda 2, and lambda 3. Performing all the computations, we have this sum of vectors, which gives rise to this vector here, the vector with components lambda 1, lambda 2, and lambda 3. As you can see, it is clear that the solution of this vector equation is given by lambda 1 equals x, lambda 2 equals y, and lambda 3 equals z. Hence, the component of every vector with respect to the canonical basis are nothing but the Cartesian coordinates of that vector. This happens only for this basis, and this is the reason why we call it canonical. Let's now see what happens if we change the order of the vectors appearing in the canonical basis. In particular, as you can see here, we consider the basis B' with the vector e3 as the first one, then we have e2, and finally we have e1. In this case, if we want to find the components of the generic vector v over 3 with respect to this novel basis, we have to write this linear combination, and we find this expression here. If you compare the novel expression with the former one, you see that these expressions don't agree because we have exchanged the vector e1 with the vector e3. Let's now discuss an example with a less simple basis of R3, this one here. We're going to see that the determination of the components of a vector with respect to this basis is associated with the solution of a system of linear equations. First of all, let's verify that this one is indeed a basis for R3. That is, U1, U2, and U3 are linearly independent and they generate R3. Let's start with the linear independence. By definition, we have to show that if we impose that the linear combination A times U1 plus B times U2 plus C times U3 equals the null vector is satisfied if and only if all the scalars A, B, and C are 0. If you write this linear combination and you perform the operation indicated here, you end up with this vector here. Then we have to impose that this vector is the null vector, whose components are of course 0, 0, 0, and we have to transform this vector equation into a system of linear equations. That means that we have to impose that A plus B equals 0, A plus 2C equals 0, and B equals 0. It is immediate to see that if we introduce the fact that B equals 0 in the first equation, we find A equals 0. And if we introduce the fact that A equals 0 in the second equation, we find that 2C equals 0, which means that also C equals 0. So, at the end, A, B, and C are all 0. That means that u1, u2, and u3 are linearly independent. Now the only thing that remains to be proven is that B second is a family of generators. That is, given any generic vector V over 3, there exist three scalars lambda1, lambda2, and lambda3 belonging to R, such that V can be written as this linear combination with vectors u1, u2, and u3. By performing the computation, we have that the vector V written as x, y, z must be equal to this vector here. So we know that this corresponds to a system of linear equations given by these ones that are written here. If you follow the substitutions that I have written in every step for the solution of this linear system, you end up with the components written here in terms of x, y, and z. In the next computation that I performed, you can see that if we introduce the components that we have just found here, here, and here, then we can reconstruct in a perfect way the original vector x, y, and z. Let's replace these abstract symbols x, y, and z with concrete numbers. I have chosen here v equals 1 to n minus 1. If you introduce x equals 1, y equals 2, and z equals minus 1 in the previous expression of the components, here, here, and here, then you find that the components of this vector here with respect to the basis b second are lambda 1 equals 2, lambda 2 equals minus 1, and lambda 3 equals 0. In fact, if you perform the linear combination of the basis vectors u1, u2, and u3 that compose b second with the scalars 2, minus 1, and 0, you perform this linear combination and you find exactly the vector 1, 2, minus 1, which was the vector v that we have started with. It is important to underline that the components of this vector with respect to the canonical basis are the Cartesian components, and so 1, 2, and minus 1. But if we consider the basis b second, then the components of this vector are 2, minus 1, and 0. And as you can see, they are completely different with respect to the canonical components. Notice now that we have analyzed three different bases of R3, B, B prime, and B second. However, there was something that remained constant in our analysis. All those bases were composed by three vectors. Was that a coincidence? Can we have bases of R3 with less than or more than three vectors? And again, is this a peculiar feature of R3, or the number of vectors appearing in every basis of a given abstract vector space must remain fixed? We're going to see next how to reply to all these questions. The most important facts regarding the number of vectors contained in a basis are stated in this theorem. Let V be a finitely generated vector space, then all the bases of V have exactly the same number of vectors. Then a family with less vectors than those of a basis can be free but can never generate V. Finally, a family with more vectors than those of a basis can generate V, but it can never be free. In particular, the first statement of the theorem assures us that we can consider as many bases of a vector space as we want, but we will always end up with the same number of vectors. They can of course change, but their number will remain fixed. For this reason, we can associate to all finitely generated vector space V a natural number called its dimension, that is precisely the number of vectors that appear in any basis of V.
We have finally arrived to the core concept of basis of a vector space. A basis V of the vector space V is an ordered free system of generators for V. This means that at the same time the vectors of V generate V, and so the span of V is equal to V, and also the vectors V1, Vn are linearly independent. That is, the linear combination written like this with generic scalars lambda 1, lambda n gives rise to the null vector if and only if all these coefficients are 0. As we have seen, the two properties together imply that every vector of V can be written uniquely as a linear combination of the basis vectors. We have also seen that when a vector space is finitely generated, then all its bases have the same number of vectors. This doesn't mean that all the bases of a vector space have the same vectors, just that the number of vectors appearing in every basis of a vector space is exactly the same. This number has a precise name and is called the dimension of the vector space.
Let's consider some examples. We start with Rn. The dimension of Rn is n because, for example, the canonical basis has exactly n vectors. To have a practical example at hand, take any natural number. I choose, for example, 7. Then in R7, we have that a collection of 6 or less vectors will never be a family of generators for R7. In the same way, a collection of 8 or more vectors in R7 will never be a family of linearly independent vectors. Let's now consider the vector space over the field F of polynomials of degree less than or equal to n in the indeterminate X. The dimension of this vector space is n plus 1. Pay attention, not n but n plus 1. The reason is that the analog of the canonical basis of Rn for this space is given by the set of these n plus 1 vectors of Fn of x. Finally, we have two extreme cases. The first, a vector space with 0 dimension, and the second, a vector space with infinite dimension. Let's start with this one. Consider any vector space V and define its null vector subspace n to be just the null vector. We are going to see that the dimension of n is 0 because a basis of n is the empty set, which is a subset of V which doesn't contain any vector, and so the number of vectors of a basis of n is 0. First of all, notice that a basis of n can have at best the null vector of V as element, but we know that the family given by the null vector itself is not free, and so will remain the only possibility that a basis of n is the empty set. To prove that the empty set is a basis for n, we have to show that the empty set is free and it is also a family of generators for n. Let's start by showing that the empty set is free. This is very easy because the empty set has no vectors, and so we cannot reconstruct the null vector of V by multiplying the elements of the empty set, which don't exist, by a non-null scalar. Instead, proving that the empty set is a family of generators for n is a little bit trickier. First of all, we have to use this theorem to identify the span of the empty set as the smallest vector subspace of V that contains the empty set. But this is, of course, the smallest vector subspace of V at all, and we know that this is exactly n. Secondly, we have to use this definition, which implies that the empty set generates n. To recap, the empty set is a free family of generators for n, and so it is a basis for n. It has 0 vectors in it, and so the dimension of n is 0. An example of non-finitely generated vector space is provided by the space of all the functions from a non-empty set X and a field F. More generally, functional spaces are among the most interesting and important infinite-dimensional vector spaces that we can find in mathematics and applications, for example, quantum mechanics. Let's consider a vector space V of dimension n and exactly n vectors of V. Then it happens that if these vectors are linearly independent, then they are also a family of generators for V. That is, they are a basis for V. On the other side, if V1, Vn generate V, then they are also linearly independent. That is, they form a basis of V. So you see that this theorem tells us that when we consider a family of vectors with the right number, that is, that of the dimension of the vector space, then we simply have to check if these vectors are either linearly independent or if they generate the vector space to check if they are a basis, because one condition implies the other. Let's now discuss a theorem related with the dimension of vector subspaces of a vector space. Consider a vector space V and these three vector subspaces. The first statement of the theorem says that if W is strictly contained in V, then its dimension is strictly inferior than the dimension of V. The second statement is a very famous formula called the Grassmann formula, and it says that the dimension of the vector space sum of these two vector spaces is given by the sum of the dimensions of the vector spaces minus the dimension of their intersection. The rigorous proof of Grassmann's formula is quite long. However, the result is intuitive. In fact, if we count the basis vectors of W1 and W2 without taking out those belonging to their intersection, then these last vectors are counted twice. This is the reason why this last term appears. Notice that when we consider the direct sum, then it means that the intersection between W1 and W2 is reduced to the null vector, hence its dimension is 0, and so we have that the dimension of the direct sum of two vector subspaces is simply the sum of their dimensions. We have almost finished chapter 1. The only sections that remain are this one, dedicated to the first practical application of linear algebra, and this one here, in which I will show you the link between vector spaces and linear maps that are the central topic of chapter 2. I prefer to discuss these two sections later and skip immediately to the section dedicated to exercises for two reasons. The first is that we have seen a lot of concepts and the exercises will surely help you test your knowledge. And the second is that I want to start chapter 2 with the motivation provided in this section here. So I invite you to go to page 34, where the exercises of chapter 1 are formulated. I will read with you the statement of the exercises and then I will provide the solution to all of them. However, I strongly suggest to pause the video and try to solve the exercises by your own before looking at the solutions. The statement of the first exercise is the following. Let E be the set of all polynomials with real coefficients in the indeterminate x with degree equal to n. So pay attention, we're not talking about the polynomials with degrees less than or equal to n. We're talking about the set of all polynomials whose degree is equal to n. The question is E a real vector space with respect to the polynomial sum and multiplication by a real scalar? As a hint for the solution of this exercise, recall that a vector space must be stable with respect to sum and multiplication by a scalar. So the answer to the question in exercise 1 is positive if all the polynomials that live in E possess this stability. Otherwise, if you manage to show that there is at least one case which shows the lack of stability with respect to one of these two operations, then E is not a vector space. The answer to the question of exercise 1, that is the set of polynomials with a fixed degree a vector space? The answer is no, because this set is not stable with respect to the operation of sum. Consider, for example, these two polynomials here. They are polynomials of degree n, as you can see. P of x is 2xn minus 1, and Q of x is minus 2xn plus 2. If we sum them together, we find that 2xn and minus 2xn erase each other, and we remain with minus 1 plus 2, which is 1. However, 1 can be interpreted as 1 times x to the power 0. So the sum of two polynomials of degree n gives rise to a polynomial of degree 0. For this reason, the sum is not a stable operation in the set of polynomials with exactly degree n. Instead, if we consider Fn of x, which is the vector space of polynomials of degree less than or equal to n, then this space contains also the polynomials of degree 0, 1, etc., up to n. For this reason, the sum is a stable operation for that vector space. Let's now deal with exercise 2. In the functional space of all the functions f from R to R, determine if the vectors given by these three functions here are linearly independent. As a hint to solve the exercise, recall that the null function is defined like this. We take any element x belonging to R, and the null function applied to x gives rise to 0. Now we use the definition of linear independence. That is, f1, f2, and f3 are linearly independent when the linear combination a f1 plus b f2 plus c f3 equals the null function is solved if and only if a equals b equals c equals 0. Remember now that functional spaces have the pointwise linear structure. So this equation here can be rewritten as this equation: a times f1 of x plus b times f2 of x plus c times f3 of x equals the null function applied to x. But as we saw before, the null function applied to any x in R gives rise to 0. Finally, notice that these expressions that you have here are written explicitly here. So you have to introduce this expression in this equation and prove that the resulting equation is satisfied if and only if A, B, and C are all null. I wrote all this in the solution, so I won't repeat it later. And as a gentle last piece of advice, let me also tell you that since A, B, and C are constant, then their values are independent of the choice of the particular x that we can consider. So I strongly invite you to see what happens in the equation that you must use to establish if the functions are linearly independent or not, when you replace x by pi half, pi third, and pi fourth. Hoping that you have tried to solve the exercise by yourself, let's see what happens when we substitute x equals pi half into this equation here. Well, we have a times the sine of pi half, which is 1, then plus b times the sine of 2 times pi half, which is the sine of pi, and the sine of pi is 0, plus c times the sine of 3 times pi half, which is minus 1. So on the left-hand side, we have a minus c, on the right-hand side 0, and so This equation tells us that A is equal to C. Thus, this result is dependent on the fact that we have chosen x equals pi half? No, because A and C are constant, so they don't depend on the particular choice of x. Here and here, you can see with all the details what happens when we substitute x equals pi third and x equals pi fourth into this equation. We have that A is equal to minus B and A is also equal to minus C. This is a very good news for us because A can be simultaneously equal to C and minus C if and only if A and C are zero. Plus, since we have A equals minus B, we have that minus B is zero, that is, B is zero. Hence, all three coefficients are zero, and so the three functions f1, f2, and f3 are linearly independent. Be aware of the fact that the technique that I just used constitutes a canonical strategy to check if functions are linearly independent or not. Let's now consider exercise 3 that you should be able to solve without any further hint. Establish if this family of vectors is a basis for R3. The most efficient way to solve this exercise is to use this theorem here. In fact, we notice that we have three vectors in R3, and this vector space has dimension 3. So, in order to test if these three vectors form a basis for R3, we need to check either if they are linearly independent or if they generate R3. It's just a matter of taste. Here I chose, in a totally arbitrary way, to test if the three vectors are linearly independent. We have seen many times that in order to check linear independence, we have to write the generic linear combination, this one, and then we have to set this combination to 0, and we have to check if the coefficients a, b, and c are all 0. If this is the case, then the vectors are linearly independent. If you perform the multiplication of the vectors by the coefficients a, b, c, and you sum what you obtain, then you have a vector equation that is equivalent to this system of linear equations. From the second equation, we obtain that a is equal to minus c. And if we introduce this information in the first and the third equation, we obtain these two equations here. If we indicate with 2 and 3 respectively these two equations, we can perform the subtraction 2 minus 3, which means that we have a 2a minus 2a plus 3b minus minus b, and so it is plus b, equals 0 minus 0, which is 0. We can see that we can erase 2a and 2a, and we remain with 4b equals 0, which of course gives b equals 0. But if b equals 0, then we can erase this term, and what we get from 2 and 3 is that 2a equals 0, that is, a equals 0. So we have a equals 0, b equals 0, and a equals minus c. So c is equal to minus a, which is 0, and also c is 0. In turn, all the coefficients a, b, and c are 0, and so these three vectors are linearly independent, and being three vectors in R3, which has dimension 3, they constitute a basis for R3. Finally, let's consider exercise 4. Establish if the sum of these two vector subspaces of R4 is direct. In order to solve this exercise, you just need to remember two things. What is the span of a bunch of vectors, and also what does it mean for a sum to be direct. Here's the solution. A sum is direct if and only if the intersection of two vector subspaces is reduced to the null vector. In this case, we are considering R4, and so the null vector is written like this. Remember that U is the span of these two vectors here, and V is the span of these two vectors here, which means that every element belonging to U can be written as a linear combination of these two vectors, and every element in V can be written as a linear combination of these two vectors. For this reason, a vector W that belongs to R4 is in the intersection between a U and V if and only if there exist four coefficients that belong to R such that W can be written both as a linear combination of these two vectors here and also as a linear combination of these two vectors here. If you perform these multiplications by a scalar and then you perform the sum, you end up with a vector equation that can be written equivalently as the system of linear equations. The first equation tells us that A is the opposite of B, and the second equation tells us that C is 2 times B. Introducing this information in the third and the fourth equation, we find these two equations here. You see that this equation and this equation are the same, and this equation tells us that C equals D equals to B. Hence, we have A equals to the opposite of B, B is free to vary in R, and C and D are equal to 2 times B. Now, as a general remark, notice that when we have a parameter free to vary in R, it is always interesting to see what happens when the parameter takes the value 0 and 1. Let's start with the value 0. If B is 0, then the vector W is the null vector of R4. In fact, if you consider B equals 0, then also A, C, and D are 0. Hence, we multiply all these vectors by 0 and we obtain the null vector. Let's now see what happens when B is equal to 1. In this case, we have that A is equal to -1, B is equal to 1, C is equal to 2, and D is equal to 2. Now, this linear combination gives rise to this vector here, which belongs to U, and this linear combination gives rise to this vector here, which belongs to V. Of course, the parameters were chosen in order to have the same vector, and as you can see, the components of this vector are not all 0. Hence, this vector is not the null vector, and it belongs to both U and V. That is, this vector, which is not null, belongs to the intersection of U and V. And for the reason that we have discussed before, the sum of U and V is not direct. Notice that in these 4 exercises we have tested your knowledge about the 3 different kinds of vector spaces that we have discussed. That is, the Cartesian power of the field R, the vector space of polynomials, and the functional spaces. Then we have also tested your knowledge about the concepts of linear combination, span, linear independence, basis, direct sum of vector subspaces, and how to transform a vector equation into a system of linear equations. So be aware of the fact that with these 4 exercises we have tested your knowledge about pretty much everything we have introduced so far. For this reason, it's important for you to check if you are able to solve these exercises without any hesitation. As I told you before solving the exercises, we're going to finish chapter 1 by discussing the first real-life application of linear algebra and then by providing the link to chapter 2. Let's start with a very nice application of linear algebra to color perception. In order to describe this application, we must recall that the human visual system is not sensible to all the electromagnetic spectrum, but only to a very tiny portion of it. The wavelengths that activate the response of photoreceptors in the human retina are those belonging to the interval between 380 and 780 nanometers, which, for this reason, is called the visible spectrum. Rays of light with different wavelengths in this interval are perceived with different colors, from red to violet, as you can see in this figure here. However, the intensity of a generic luminous signal doesn't depend only on one single wavelength, but on all the wavelengths of the visual spectrum, and it can be modeled as the following function. The general name used to indicate this function is light spectrum, and the vector space that contains it has infinite dimensions. If human color perception would be based only on the physics of light spectra, then color pictures, cinema, TV, and color printing would probably be impossible or at least much more difficult to realize. Instead, the human visual system has a peculiar feature. The photoreceptors in the retina have three different sensitivity curves picked on the long, middle, and short wavelengths of the visual spectrum, as you can see in this figure here. At first sight, the fact of not being able to sense all the wavelengths of light in the same way could be thought as a sort of physiological defect. But, on the contrary, it is a very welcome feature, because it allows us to perceive colors only on the base of three dimensions instead of infinitely many. As I told you in the historical introduction to Chapter 1, Grassmann wasn't only a mathematician, but he had interest in lots of disciplines, and he used his own discovery, linear algebra, to show that perceived colors were contained in a vector space of dimension 3. Thanks to Grassmann's discovery, and also to those of other very important scientists who lived at the same time, such as Maxwell and von Helmholtz, the so-called RGB technology could be developed in the 20th century. Color perception is still a very active research field, and we don't have the time to discuss it further in this course. However, I thought that it was important to tell you that Grassmann, only 12 years after the publication of his book, in which he gave the first formalization of linear algebra, was able to use it for practical purposes. This should give you a hint of how important linear algebra is in practical applications. But in order to see that in a meaningful way, we need to develop the concepts that are contained in Chapter 2 and 3. We have arrived to the end of Chapter 1, and as I told you, I want to link the theory of vector spaces that we have studied in this chapter with that of the so-called linear transformations that we're going to study in Chapter 2. The first piece of information that we need in order to build this link is provided by this theorem here. Let's consider a vector space V of dimension n over the field F, a basis B of V, and two vectors v and w, whose components with respect to the basis B are given by the scalars lambda1, lambda n, and mu1, mu n, respectively. Then, with a direct computation, it can be proven that the components of the sum of these two vectors are given by lambda1 plus mu1, etc., lambda n plus mu n. Similarly, we can verify that given any scalar A belonging to the field F, we have that the components of A times V are simply the original components of V multiplied by A. The second piece of information that we need is the realization that we can use the uniqueness of the association between a vector and its components with respect to a basis to build a well-defined function, this one here. Since every vector V can be associated only with one specific set of components with respect to the basis B, then there is no ambiguity in defining this function between any vector space V and a particular one, Fn. Thanks to the theorem that we have quoted above, we have that the association between V and Fn established by the function Fb has the following two properties. The first is that Fb applied to A times V is A times the components of V, namely A times Fb of V. The second property is that Fb applied to the sum of two vectors is simply the sum of the components of the two vectors, namely the sum of Fb applied to V and Fb applied to W. These two properties are exactly those that define a linear map that is the object that is discussed in Chapter 2. Before passing to the study of Chapter 2, I strongly invite you to test your knowledge about the concepts that we have treated in Chapter 1 by answering the questions reported below and trying to solve again the exercises presented before.
We have just seen that thanks to the concept of basis, we can smoothly pass from Chapter 1, dedicated to the study of vector spaces, to Chapter 2, dedicated to the analysis of linear maps between them. The study of linear maps is totally natural in linear algebra. In fact, each time we fix a basis, we give rise to a function. That is, the function that takes any vector v to the set of its components with respect to the basis. We have seen that this function is not only well defined but also linear. We will study in a thorough way the concept of linearity in Chapter 2. For the moment, just keep in mind that this function is linear because it brings linear combinations of vectors into linear combinations of their components. There is a sort of non-written rule in mathematics which, however, turns out to be true almost all the time. This rule says that when an object appears naturally from the study of another concept, then this object turns out to be useful and important. In our case, we have just seen that linear maps emerge naturally from the study of vector spaces, so we expect them to be useful and important. We are going to verify this in Chapter 2 and 3.
At the end of Chapter 1, we have motivated the interest about linear functions, which are those that behave well with respect to linear operations in a sense that will be detailed in this chapter, where the most important properties of such functions will be outlined. Before dealing with all this, we must clarify that for historical reasons, in the jargon of linear algebra, the word function is replaced with application or for short map. However, even if the name changes, the underlying concept is exactly the same. Consider two vector spaces V and W, not necessarily different but both defined over the same field F, and consider this linear combination here. Then take a map F from V to W and apply this map to V, that is, write this. Since here we have a linear combination, the only way in which F can pass through the linear combination is to have something like this. That is, F passes through the linear combination if the position of F can be swapped with the position of the sum and the scalars lambda j. If we write the sum explicitly, then this last equality can be written as follows. The two defining features of this equality can be understood by considering n equals 1 and n equals 2. When n equals 1, then this formula becomes f of lambda 1 v1 equals lambda 1 f of v1. This is called homogeneity of f. So you see that homogeneity simply means that when f is applied to a vector multiplied by a scalar, then we can take off the scalar. Considering now n equals 2 and lambda 1 equals lambda 2 equals 1, we have that this formula reduces to f applied to the sum of v1 and v2 is the sum of f applied to v1 and applied to v2, a feature that is called additivity of f. The formalization of a linear map is as follows. Consider two vector spaces V and W. They can be the same or they can be different, but they must be defined over the same field F. Then a map F from V to W is said to be linear if it is additive and homogeneous in the sense defined before.